So welcome to lecture 4 of electric potential and capacitance. So in the previous lectures we have completed the talk about electric potential, then we discussed about electric potential energy for the charge system. We also dealt with the potential of the dipole and we dealt with the concerned numericals about them. So now we will be discussing about capacitance. So we are dealing with the capacitance and capacitors. So basically capacitors is a device that stores or rather condenses electrostatic field energy. So capacitors provide a temporary storage of energy in the circuits and can be made to release the energy when required. Now the property of the capacitor that characterizes its ability to store its energy is regarded as the capacitance of the capacitor. When the energy is stored in a capacitor, an electric field exists within the capacitor. So let us begin our study with the study of an isolated conductor and we will be calculating its capacitance. So we are dealing with an isolated conductor. So if we consider an electrical conductor such as maybe of a metal which is holding charge at its surface. So if it is a spherical conductor of radius r, then I can say that the equation of potential is equal to kq by r, where r is the radius of the spherical conductor. So this tells us that the potential of an isolated spherical conductor is directly proportional to the charge. So this equation which is stating that V is proportional to Q, the ratio of the charge given to any isolated conductor and its potential rise, that is I say that the value of Q by V is a constant. Now this ratio of Q by V is regarded as the capacitance of the capacitor. So this ratio of Q by V is regarded as C, which is equal to capacitance of the capacitor. So if we are considering an isolated sphere, so I can say that the potential V is equal to 1 upon 4 pi epsilon naught r into Q, and the ratio that is Q by V is equal to 4 pi epsilon naught r. So this is going to be the capacitance of an isolated spherical capacitor. So this is going to be the capacitance of an isolated spherical capacitor. So now let us discuss about the unit system. So the capacitance of the capacitor is measured in farad. So it is also pronounced as farad. So over here I say if this is capacitance, so I can say that if the charge is 1 coulomb and the value of potential provided is 1 volt, so we refer this as equal to 1 farad. So over here the point which is to be noted is 1 farad is a very large unit. 1 farad or 1 farad is a very large unit. So in order to understand this, so let us take a small illustration. So we will be using this formula which we have obtained, that is the capacitance of an isolated spherical capacitor. So if we consider that earth which is of radius 6400 kilometer, that is 6.4 into 10 to the power 6 meter, is an isolated spherical capacitor. So we can calculate the capacitance for the earth, that is equal to C is equal to 4 pi epsilon naught r. So if we wish to do this calculation, we write it as 1 upon 9 into 10 to the power 9 into radius, which is 6.4 into 10 to the power 6, and the value will be in farad. So on calculating this, we obtain 711 into 10 to the power of minus 6 farad. So considering the entire earth also, we failed to produce a value of 1 farad, and over here now I think it is concluded that 1 farad is a very large unit. So we have placed the entire planet in the place of the capacitor. Our entire planet is insufficient to produce a capacitance of equivalent to 1 farad, and hence I say that the capacitance equal to 1 farad is a very large unit. So in our general practice, so in general practice, we consider smaller units, and the smaller units which we consider are generally equal to 1 microfarad, which is equal to 10 to the power minus 6 farad. We consider 1 nanofarad, which is equal to 10 to the power minus 9 farad. We consider as 1 uh, picofarad. So where 1 picofarad is equal to 10 to the power minus 12 farad. So all these unit systems are generally employed for the calculation of capacitance of the capacitor. So the first example of the capacitor which we are going to take is the example of a parallel plate capacitor. So let us study about the parallel plate capacitor. So while considering electric field due to infinitely large plate, in chapter 1, I already gave an introduction as to what a parallel plate capacitor will be actually looking like. But once again, for the sake of derivation, I am doing that, performing that derivation one more time. So if we consider that two infinitely large plates are placed close to each other, so considering that this is having plus q charge and the other plate is having minus q charge, having the same surface area, and hence the value of surface charge density is plus sigma and minus sigma for them. So I consider that the positive charge is uniformly spread throughout the plate, and the negative charge is spread throughout the plate in a uniform way. So I say that electric field due to a single plate, so electric field due to an infinitely large plate is calculated as sigma by 2 epsilon naught. So if we consider this value, that is sigma by 2 epsilon naught, we consider in this way that the value of electric field due to the positive plate is directed away. So the value of electric field is directed away. So the value of electric field due to the positive plate is directed away on the right and the left hand side, and also in between the plate. And this value is independent of the distance, and hence we write it as sigma by 2 epsilon naught everywhere. Now due to the negatively charged plate, the electric field is directed towards the negatively charged plate. So it is directed towards the negatively charged plate, and it is directed towards the negatively charged plate, and the value is still the same, that is sigma by 2 epsilon naught. So if we calculate the net value of electric field, so over here the net value of electric field is cancelling each other out and the value is 0. On the right hand side of the plate is again they will cancelling each other out and the net field is 0, and in between the plate the electric field is added together to produce a strong electric field which is equal to sigma by epsilon naught. So basically we have added the electric field due to the positive and the negative charge to produce the electric field equal to sigma by epsilon naught. Now at the corners of the plate the electric field will fringe, and this is regarded as fringing effect. So this is regarded as fringing effect. At both the corners the electric field is going to fringe and it is regarded as fringing effect. So the separation of the plate is very small compared to their size. So if we do so, the fringing of the electric field at the edges is slightest. So if we decrease the separation of the plate in comparison to their size, so the fringing of the electric field at the edges is slightest. So we calculate that the net electric field in between the capacitor is equal to sigma by epsilon naught. That is the sum of the electric field by the positive and the negative plate. So since this value is a constant, so if I consider that the potential difference between the plate is V, so if V is potential difference between the plate, then we can say that V is equal to E into D, where D is separation between the plates of the capacitor. So now we can write it in this way, that V equals sigma by epsilon naught into D, and we can place sigma as charge upon area, so Q by A epsilon naught into D, and again we have attained that C is equal to Q by V. So the value of Q by V over here is attained as epsilon naught A by D. So the value of capacitance of a parallel plate capacitor is equal to epsilon naught A by D, and the relation which we use, that is Q is equal to CV, is also very important. So these are the few notable formula which we have learned, that Q is equal to CV, or the capacitance C is equal to Q by V. And the next which we learned over here is C is equal to epsilon naught A by D, where A is area of the plate and D is the separation between the plates. So let us move to understand the another aspect. So we will be calculating the capacitance for a spherical capacitor. So let us take another example. So we are taking example of a spherical capacitor. So over here we are considering two concentric spherical shells of radius A and B. That is, A is the inner radius and B is the outer radius. So A is the inner radius and B is the outer radius, and a positive charge plus Q is distributed on the inner shell. So it is going to reside on the outer surface of the shell A, and a charge minus Q is going to be induced. So we are saying that first of all a positive charge is spread on the surface of the shell A, and as a result of which a negative charge is induced on the inner surface of the shell B. So where we have taken that the internal radius as A and B respectively. And again a positive charge is going to be induced on the outer surface of the shell. So in order to prevent that, we are earthing the outer surface of the shell. So a charge plus Q will flow from the outer shell to the earth. So if we consider a Gaussian surface at a distance r which is greater than A but less than B, so we are considering a Gaussian surface somewhere here. at a radius r which is greater than a but less than b. So over here I write that the charges enclosed is going to be plus q, and if I use Gauss law, so we can say E dot A is equal to q enclosed by epsilon naught, and the value of electric field can be calculated in this way: 4 pi r square is equal to q by epsilon naught. So that is, we obtain the value of electric field as q upon 4 pi epsilon naught r square. Let us make this also capital Q. So this is going to be the expression which we have for the electric field, which is in the space between the inner and the outer radii A and B. So if we move with the formula of potential, that is VA minus VB is equal to negative integral of E dot dr from A to B. So we can use it in this way, that the value of potential difference, since we are equating the surface B to 0, so we say that VB is equal to 0, and I will write the potential V is equal to Q upon 4 pi epsilon naught R square dr B and A with a negative sign. So if we solve this, we obtain Q upon 4 pi epsilon naught, and integration of 1 by r square is minus 1 by r, and if we adjust it with the minus outside, so we write it as minus 1 by a minus 1 by b. So we obtain q upon 4 pi epsilon naught ab, and over here it will be b minus a. So this is the value which we have obtained. So from here, if we calculate the value that is equal to q by v, so I can again rewrite this equation, that V is equal to Q B minus A upon 4 pi epsilon naught AB, and if we calculate the capacitance C, that is Q by V from here, so we can write it as 4 pi epsilon naught AB by B minus A. So this is the value of capacitance of a spherical capacitor with inner radius A and outer radius B. If we again consider this expression one more time, that this expression, so over here in this expression, if I put that b approaches infinity, so in this expression if we write b approaches infinity, so we can say that 1 by v will become equal to 0, and then we will be left with q upon 4 pi epsilon naught a. So if you are understanding clearly, so you will end up writing in this way, that you will obtain the expression like this. So if b approaches infinity in the previous expression, so we'll obtain v is equal to q upon 4 pi epsilon naught a, and hence we write the capacitance C, which is equal to q by v is equal to 4 pi epsilon naught a. That is the capacitance of an isolated spherical capacitor, the point from where we initiated the chapter. So I think this derivation is absolutely fine for you. So with this we come to the study of cylindrical capacitor. So let us begin by understanding cylindrical capacitor. So we are considering coaxial cylinders of radius A and B, such that B is greater than A. So I am drawing it in this way, that this is the inner cylinder having radius A, and then we have a outer portion of radius B, which we are drawing like this. So the cylindrical capacitor is looking like this. So it is having an inner radius A and outer radius B. And we are saying that the outer surface is earth. So just like the previous case, we will be taking that VB is equal to 0. So the charging is done in such a way that the inner surface acquires a positive charge throughout it with a value of plus lambda, that is lambda charge per unit length, and the inner surface of the outer cylinder acquires a charge distribution of minus lambda with a negative charge distributed over its length. And we are considering that the total length of the cylindrical capacitor which we are taking is equal to L. So if we consider a Gaussian surface at a radius r which is greater than a but less than b, so we will say that the charges enclosed by this cylindrical Gaussian surface will be, so q enclosed will become equal to lambda into L. So the charges enclosed will become equal to lambda into L, where lambda is charge per unit length. So if we apply Gauss law, so over here we will attain cyclic integral of E dot A is equal to Q enclosed by epsilon naught, and we will attain a equation like E into 2 pi RL. So we are taking the curved surface area because only in this case the electric field will be parallel to the curved surface area, whereas on the upper and lower end the electric field is perpendicular to the area vector. So they will not produce to E dot A, they will not contribute to E dot A, and this is written as lambda L upon epsilon naught. So from here we can chop out L and we obtain electric field which is equal to the same equation as infinite line charge, that is E is equal to lambda upon 2 pi epsilon naught r. So if we put this in the equation, that is VA minus VB is equal to negative integral of E dot dr. So we can put it in this equation and we obtain over here that V is equal to, since VB is equal to 0, so we get V which is equal to lambda upon 2 pi epsilon naught. So it is constant and will come out of the integration 1 by r dr. This is B and this is A. So over here we say that the value of 1 by r is equal to ln r. So and if we put the minus sign in, so we write it as ln b by a, and hence the equation from here will come out as v is equal to lambda upon 2 pi epsilon naught ln b by a. So if we put lambda as charge per unit length, so we can write from here that v is equal to q upon 2 pi epsilon naught L into ln b by a. So the value of capacitance, that is C, which is equal to Q by V, can be written in this way, that 2 pi epsilon naught L upon ln of b by a. So this expression is the capacitance of the cylindrical capacitor, that is C is equal to 2 pi epsilon naught L upon ln b by a. So now let us look at the energy profile or the energy stored in a charged capacitor. So we are dealing with the energy stored in a charged capacitor. So if we consider the energy stored, so we can say that if suppose we consider that there are two parallel plate capacitor and a charge dq is brought from the plate 1 from plate 1 to 2. So we are considering something like this. So we are considering something like this, that a charge dq is brought from plate 1 to plate 2. So if this charge dq is transferred from one plate to the another, let us say against the electric field E, which is in this direction, so I can write that the work done is written in this way: work done is equal to E into D, that is the value of potential, into dq. So we write from here that this work done, where V can be written as Q by C. So we write it in this way, that this is equal to V dq, and we can write V is equal to Q by C. So if we write it as Q by C dq, so this value of work done will give us the value of energy stored, W, which is equal to Q square by 2C. So it can also be regarded as the work done by the battery in sending a charge capital Q to the capacitor. So we are obtaining a equation from here that the value of work done or the energy stored in the capacitor is equal to Q square by 2C, and can also be understood as the work done by the battery in sending a charge Q. So if we consider this equation that Q is equal to CV, so if we put Q equal to CV over here, we will end up getting the equation half CV square. So the work done at the expense of the chemical energy of the battery is stored in the capacitor in the form of electrostatic field energy having value Q square by 2C, or half CV square. Now over here I would like to add a point as to when we use this formula, or when are we going to use the other one, that is half CV square. So if we consider a case in which the capacitor is connected to a battery, so if the plates of the capacitor are connected to the battery, so we will say that the battery is providing a potential difference which is equal to constant and having a capacitance C. So we use the energy equation half CV square, because in this case the value of V, that is the potential difference supplied by the battery, is not changing. And if in case we say that the capacitor is isolated, that is the charge on the plates of the capacitor is constant. So let us say that there is a positive charge on the upper plate and a negative charge on the lower plate. So in this case, we say that when the charge is constant on the plates of the capacitor, so we use the expression Q square by 2C. So this is in, we can say when the battery is connected, we use this expression, and with battery disconnected, we use the other equation. So now we will be studying about the introduction of dielectrics, and before that we will be studying about the nature of dielectric, as to what is dielectric. So let us begin with the discussion on dielectrics, and followed by that we will be studying polarization. So we are studying dielectrics and polarization. So listen very carefully, because I am not writing most of the points. I am just stating every bit possible. So take down proper notes while listening to this. So whenever we use the word dielectric, so dielectric is basically implying an insulator. So for example, glass, wood, they all are form of a dielectric. So a dielectric is a non-conductor up to a certain value of the electric field. So up to a certain value of electric field, they are non-conductors. And if a very high electric field is created in a dielectric, the outer electrons of the insulators or the bad conductors will get detached from their parent atom. So let us first of all understand why something is an insulator and why something is a conductor. So we say if there is a presence of large number of carriers, which is generally electron when we are considering a solid. So we say that if there is a large number of free electrons in a solid conductor, then it is a conductor. But if in case there is the large number of carriers are missing, that is there are only few electrons available in the form of carriers, then we say that the substance is an example of an insulator. But the less amount of carrier electrons doesn't imply that the substance doesn't contain electrons. The electrons which are there is attached to the atom. And hence, when a very high electric field is created in a dielectric or an insulator, the outer electrons may get detached from their parent atom. And as a result of which, the dielectric will behave like a conductor, and this phenomena is regarded as dielectric breakdown. Dielectric breakdown, and the maximum value of the electric field or the potential gradient that the dielectric material can tolerate without its dielectric breakdown is regarded as the dielectric strength of the medium. Is regarded as the dielectric strength of the medium. So I am repeating that last part again. When we apply a very high electric field, so then what happens? The outer electrons may get detached from the parent atom of the insulator, and as a result of which they start behaving like a conductor. So the maximum value of the electric field or the potential gradient that a dielectric material can tolerate without electric breakdown is regarded as the dielectric strength of the medium. So dielectric strength of the medium is measured in volt per meter. So it is measured in volt per meter. Now the another part which we are supposed to understand is that the dielectric is categorized in two ways. So dielectrics are classified in two ways. One is an example of a polar dielectrics, and the another one is an example of non-polar dielectrics. So when we say that something is a polar dielectric, so it implies that even when electric field or an external electric field is not present, this substance is going to have a certain degree of polarization. So over here, we can also say that the poles are already generated, that is, the material is already having its own polarization. So this is how they look like. Or we also state it in this way that a polar dielectric is a substance in which the center of the positive charges do not coincide with the negative charges. So the center of the positive charges and the center of the negative charges are not coinciding with each other. So now what will happen if we say that an electric field is applied? So when the electric field is applied in the polar dielectric, they orient themselves in the direction of electric field. So they orient themselves in the direction of electric field only when an external electric field is applied. Otherwise, they are randomly oriented without producing any polarization because they will be like random vectors. So all the polar covalent bond materials can be regarded as example of polar dielectrics. When we say non-polar dielectrics, so over here I can say that the center of the positive charges and the center of the negative charges coincide with each other when no electric field is applied. And when an electric field is applied, the positive charge experiences a force in the direction of electric field, and the negative charge experiences a force in the direction opposite to the field, and as a result of which the substance produces an induced electric dipole. So I write they generate an induced electric dipole. So this is how we understand the nature of dielectric. Now let us understand the another concept which is regarded as the polarization of dielectric followed by the dielectric constant. So if we consider that dielectric is inserted between the plates of the capacitor or maybe in an external electric field. So let us consider something like this, that this one is a uniform positively charged plate of the capacitor and the another one is a uniformly negatively charged plate of the capacitor in which an electric field E is present. Now we introduce a dielectric substance somewhere here in between the plates of the capacitor. So if we introduce a dielectric substance, so now what is going to happen? An induced. So over here, unlike conductors where the identical charge is created on the face of the conductor, over here a slight negative charge will be induced and a slight positive charge will be induced on the opposite face as shown. So as a result of which an electric field is induced inside the material of the dielectric. So now this induced electric field is not strong enough to nullify the complete electric field inside the dielectric, but it certainly reduces the effect of the externally applied electric field E. So I say that the charge induced on the dielectric can be considered as Q induced negative on this surface and positive Q induced on the other end of the surface. And the net value of electric field which is present inside the dielectric can be written as the external electric field minus the value of induced electric field due to the polarization of the dielectric. So now we define the dielectric constant of the medium. So a dielectric is having another parameter which is regarded as the dielectric constant. So we have considered over here that an original electric field E was present. So the dielectric constant is the factor by which the electric field inside the dielectric get reduced. So the resultant electric field inside the dielectric will become or will get reduced by a factor of k, or it is also designated as epsilon r. So k and r are representing the same thing, that is dielectric constant of the medium, and is also known as the relative permittivity of the material. So it is the factor by which the electric field inside the material of the dielectric gets reduced when it is placed in an external electric field. So this K is regarded as the dielectric constant of the medium, and the net value will become or will get reduced by the factor of K when the original induced field is E. So over here I can say that in this expression we can write it as E by K is equal to E minus E induced, and from here we obtain the value of E induced is equal to E 1 minus 1 by K. So this is the value which we have attained for the direction of induced electric field inside the material of the dielectric, and the net value of electric field will become E by K. So if we substitute the electric field with the expression sigma induced by epsilon naught is equal to sigma original by epsilon naught 1 minus 1 by K. So we further get from here that Q induced by A epsilon naught is equal to Q naught, or the original charge on the capacitor, divided by A epsilon naught 1 minus 1 by K, and from here we attain the equation for induced charge on the surface of the dielectric, that is Q induced is equal to Q naught 1 minus 1 by K. So this is how we understand the principles of or the working of dielectric. So what is to be kept in mind is that the dielectric constant for vacuum is equal to 1. So for vacuum we also consider the value equal to 1 for air. For vacuum the dielectric constant is equal to 1, and the value of dielectric constant is always greater than 1. So K is always greater than equal to 1, where 1 is the value for vacuum. For water, the dielectric constant is 80.